Imagine waking up tomorrow and discovering that you have already lived this day before. Not in a dream, not in a movie, but according to the laws of physics themselves. You check your watch, you feel time moving forward, yet deep inside the equations of Einstein, time is not what your instincts tell you it is. In fact, modern science quietly admits something shocking. Time travel is not forbidden, it is allowed. But there is a catch. Nature seems to have a deep hatred for the past. When we speak about time, we instinctively imagine a river flowing in one direction, carrying us helplessly from the past into the future. This intuition is so deeply wired into our daily lives that it feels unquestionable. You wake up, the clock ticks forward, memories accumulate behind you, and the future remains unwritten. Yet, physics, when stripped of human intuition and rewritten in the language of mathematics, tells a far stranger story. Time, according to modern science, is not a rigid, universal metronome ticking away in the background of reality. It is flexible, dynamic, and deeply intertwined with space itself. This realization did not come from philosophy or speculation, but from one of the most revolutionary scientific insights in human history, Einstein's theory of relativity. Once time became a physical quantity that could stretch and bend, the idea of time travel stopped being science fiction and quietly entered the domain of serious science. In classical Newtonian physics, time was absolute. It ticked at the same rate everywhere in the universe, whether you were standing still or racing through space, whether you were on Earth or at the edge of the cosmos. This comforting simplicity collapsed in 1905, when Einstein showed that time depends on motion. The faster you move through space, the slower you move through time. This is not a metaphor or a clever analogy. It is a direct consequence of the structure of the universe. Space and time fuse into a single fabric known as space-time, and motion through one affects motion through the other. Once this door was opened, physicists realized that time is not merely something we experience, but something that can be manipulated under the right conditions. This immediately forces us to confront a profound idea. If time can slow down, then observers can experience different amounts of time between the same events. Two people can separate, reunite later, and find that they've aged by different amounts. That alone is enough to shatter the everyday notion of time as universal. More importantly, it establishes the foundation for time travel into the future. If you can experience less time than the rest of the universe while events continue unfolding around you, then you are effectively moving forward in time relative to others. You are not skipping moments subjectively, but objectively arriving in a future that others reach through normal passage. This is where the idea stops being theoretical and becomes experimental reality. Time dilation has been measured countless times with exquisite precision. Atomic clocks placed on fast-moving airplanes tick more slowly than identical clocks left on the ground. GPS satellites orbiting Earth at high speeds and weaker gravitational fields must constantly correct for time dilation effects, or your phone's location would drift by kilometers each day. Nature does not negotiate with philosophy. The equations work, the measurements confirm them, and the conclusion is unavoidable. Time travel to the future is already built into the laws of physics. Now imagine taking this principle to its extreme. Instead of flying on an airplane, suppose you board a spacecraft capable of traveling close to the speed of light. As your speed increases, time for you slows dramatically compared to the outside world. At 90% the speed of light, the effect becomes noticeable. At 99.9%, it becomes astonishing. A journey that feels like a few years to you could correspond to decades or even centuries passing on Earth. You return home to a planet that has aged far beyond your personal timeline. You have leapt into the future not by magic, but by obeying the equations of relativity with ruthless precision. What makes this so unsettling is that there is no known physical law that forbids this. The limitation is technological, not theoretical. The energy required to accelerate a massive object close to the speed of light is enormous, bordering on the unimaginable with our current capabilities. But physics does not say no, it simply says pay the price. If a future civilization mastered energy on a stellar or galactic scale, time travel to the future becomes not just possible, but routine. In this sense, the future is wide open. It welcomes travelers willing to obey the constraints of nature. The second great pillar supporting this idea comes from gravity itself. Einstein later realized that motion is not the only thing that affects time. Gravity does as well. Massive objects warp the fabric of space-time, and time slows down in regions of stronger gravitational fields. This means that clocks tick more slowly near massive bodies than they do far away. Again, this is not speculation. It has been measured directly. Clocks placed at higher altitudes tick faster than those at sea level. Even the tiny difference in gravity between your head and your feet produces a measurable time dilation, though far too small for human senses to detect. Once again, nature reveals a pathway to the future. If you could hover near an extremely massive object such as a neutron star or a black hole, time for you would slow dramatically relative to the rest of the universe. From your perspective, your watch ticks normally, your thoughts proceed at their usual pace, and nothing feels unusual. But far away, stars age, civilizations rise and fall, and the universe evolves while you remain almost frozen in time. When you eventually return to safer regions of space, you emerge into a distant future that you did not personally experience step by step. This leads to one of the most astonishing realizations modern science has to offer. The universe already contains natural time machines. They are not devices built by engineers, but cosmic structures formed by gravity itself. Black holes, in particular, represent the ultimate expression of this effect. Near the event horizon of a black hole, time slows to a crawl relative to the outside universe. To a distant observer, an object falling toward the horizon appears to freeze in time. To the falling observer, time continues normally, but the rest of the universe accelerates wildly. The beauty of this picture lies in its consistency. There are no paradoxes here, no contradictions, no violations of causality. Cause still precedes effect. Information still flows forward in time. Physics remains calm, elegant, and internally coherent. This is why science allows time travel to the future so comfortably. It emerges naturally from the structure of space-time and aligns perfectly with everything we know about motion, gravity, and energy. What is perhaps most humbling is that this means we are all time travelers already, just at an extremely slow rate. Every second, we move 1 second into the future. Change the conditions, increase the speed or the gravity, and the rate changes. Time is not a rigid dictator, it is a negotiable parameter. The universe does not object to this negotiation. It enforces the rules, but within those rules, the future remains accessible. This realization reshapes how we think about destiny and progress. The future is not a forbidden realm sealed off by cosmic law. It is a landscape we are already moving toward, and under the right conditions, we can move toward it faster than others. Science does not flinch at this idea because it preserves the logical structure of reality. The future has not happened yet from the perspective of the traveler, and when it arrives cleanly, without contradiction. And so, within the cold, precise language of equations, physics quietly whispers something extraordinary. Time is not a prison, it is a dimension. You may bend it, stretch it, and move through it at different rates. The universe permits this without protest, as long as you respect the deeper architecture of space-time itself. Once we turn our gaze away from the future and attempt to face the past, the tone of physics subtly but unmistakably changes. The equations still exist, the mathematics still functions, but an uneasiness enters the picture, as if nature itself is warning us that we are stepping into dangerous territory. Traveling into the past is not merely a faster or slower version of moving forward. In time, it challenges the very foundation upon which reality is built. cause and effect, memory and identity, logic and consistency all suddenly find themselves under threat. The moment backward time travel enters the conversation, physics does not collapse, but it becomes deeply suspicious. The core of the problem lies in paradox. Not dramatic Hollywood paradoxes, but quiet, devastating, logical ones. If you travel into the past and alter an event, even slightly, you risk unraveling the chain of causality that led to your journey in the first place. The universe depends on a consistent ordering of events. Causes must come before effects. Break that rule and the universe loses its narrative coherence. This is not a philosophical preference. It is embedded into how physical laws operate. When equations describe reality, they assume consistency. The past, once altered, threatens that consistency. Consider what happens if cause and effect become circular rather than linear. An event happens because of itself, or fails to happen because it already happened. Physics has no tolerance for self-contradictory histories. You can write down equations that allow backward time motion, but when you apply them to real situations involving information, decisions, and interactions, the logical structure begins to fray. Nature seems to permit strange things, but not nonsense. And paradox is, in the language of physics, a form of nonsense. This is why the past feels different from the future. The future is open, undefined, and probabilistic. The past is fixed, recorded, and constrained. Every atom carries a memory of where it has been, every photon a trace of its journey. To tamper with the past is to tamper with an enormous archive of information encoded into the structure of the universe. The deeper we look, the clearer it becomes that the past is not simply early time, but a stabilized configuration of reality that resists interference. Yet, intriguingly, Einstein's equations themselves do not forbid backward time travel outright. Certain solutions allow paths through space-time that loop back on themselves. These closed time-like curves exist mathematically and arise naturally in extreme conditions. This creates an unsettling tension. The laws of physics open the door, but reality seems reluctant to let anyone walk through it. The universe appears to allow the idea, but sabotage its execution. This tension becomes even more pronounced when we consider wormholes. Wormholes emerge naturally from the equations of general relativity as bridges connecting distant points in space-time. In principle, they could connect not only different regions of space, but different moments in time. If one mouth of a wormhole experiences time differently than the other due to motion or gravity, a traveler passing through could emerge in the past. The blueprint exists, the mathematics works, the temptation is enormous, but the universe responds by raising the cause. To keep a wormhole open, one needs exotic matter with negative energy density. This is not ordinary matter, not antimatter, but something far stranger. While tiny amounts of negative energy appear in quantum effects, sustaining a macroscopic wormhole would require controlling it on scales far beyond our current understanding. It is as if the universe permits wormholes in theory, but hides the key behind layers of extreme physics. Even if such a wormhole could be stabilized, another problem arises. The moment it becomes a time machine, quantum effects begin to intensify. Radiation builds up, instabilities grow. The closer you come to creating a pathway into the past, the more violently the equations respond. Instead of smoothly allowing backward travel, the system destabilizes, threatening to destroy the wormhole itself. This behavior is not accidental. It suggests that the universe has a feedback mechanism, one that amplifies disturbances when causality is endangered. This is where quantum physics enters the story, not as a savior, but as an enforcer. At the smallest scales, the universe is governed by probabilities and fluctuations. These fluctuations are usually harmless, averaging out over time, but near a time machine, they can become catastrophic. Virtual particles can pile up, energies can spike, and the delicate structure required for backward time travel collapses. The equations themselves seem to conspire against the traveler. What emerges from this picture is not a simple prohibition, but a kind of cosmic immune system. Time travel to the past is not stamped illegal by physics, but every attempt to realize it triggers defensive responses. Instability energy divergence, and quantum chaos rise up as barriers. The universe does not shout no, but it whispers not so fast, again and again, until the project becomes impossible to sustain. This raises a profound possibility that the laws of physics are self-consistent not because backward time travel is impossible in principle, but because the universe actively preserves consistency. Reality may allow many strange pathways, but only those that do not destroy its logical structure can remain stable. In this view, the past is protected not by decree, but by dynamics. The universe does not hate curiosity, but it hates contradiction. Yet, even here, physics offers a subtle escape hatch. Quantum theory hints that the universe may be far larger than we perceive, containing multiple histories rather than one. In such a framework, traveling to the past does not overwrite history, but branches it. You do not change your past, you create another. The paradox dissolves not by forbidding action, but by multiplying realities. The equations remain consistent, and causality survives within each branch. This idea is unsettling, but it aligns with the deepest insights of quantum mechanics. The universe, at its core, may be far more flexible than our everyday experience suggests. But even in this vast landscape of possibilities, the original past remains untouched. It is preserved, isolated, and stable. Once again, the pattern repeats itself. The future may be explored, the present may be navigated, but the past stands as a completed chapter, protected by the architecture of reality itself. And so, as we descend deeper into the physics of time, a clear asymmetry emerges. The future invites movement, experimentation, and exploration. The past resists, not out of malice, but out of necessity. The universe seems to understand that without a stable past, there can be no meaningful future at all. As we probe deeper into the question of why the universe resists travel into the past, we begin to see that this resistance is not emotional or philosophical, but structural. One of the most compelling ideas to emerge from this investigation is that the universe may possess a built-in mechanism to defend its own timeline. This is not science fiction. It is a sober inference drawn from the mathematics of general relativity and quantum mechanics when they are pushed to their limits. The closer physicists come to constructing a scenario in which the past can be altered, the more violently the equations react, as if reality itself were tightening its grip to prevent a breakdown of order. This insight was crystallized by the idea that the universe enforces a kind of self-consistency. When time loops back on itself, strange things begin to happen to energy and information. Fields fluctuate uncontrollably. Radiation intensifies without bound. The calm, predictable behavior of spacetime gives way to runaway effects that threaten to tear the system apart. These are not minor inconveniences that clever engineering might solve. They are fundamental instabilities rooted in the quantum structure of reality. The universe does not politely object to backward time travel, it destabilizes it. This is where the notion of chronology protection becomes unavoidable. The idea is simple, yet profound. The laws of physics may conspire to prevent violations of causality, not by banning them outright, but by making them physically unsustainable. As soon as a region of space-time begins to resemble a time machine, quantum effects surge, destroying the delicate conditions required for backward travel. It is as if the universe allows you to approach the edge of paradox, but never to cross it. What makes this so compelling is that this protection does not appear to be imposed externally. There is no cosmic referee blowing a whistle. Instead, the instability arises naturally from the interaction between gravity and quantum mechanics. Vacuum fluctuations, normally tiny and harmless, become amplified near closed loops in time. Energy densities skyrocket. The equations that once seemed to allow backward travel now generate infinities, a clear signal that the model has broken down. In physics, infinities are nature's way of saying that something has gone terribly wrong. This suggests that the universe is not passively obeying rules, but actively maintaining coherence. Causality is not just a feature of our experience, it may be a dynamically protected principle. Without it, prediction collapses. Memory loses meaning and identity dissolves. The universe, it seems, cannot function in such a state. And so any attempt to engineer a pathway into the past triggers the very forces that destroy it. Yet the story does not end with prohibition. Physics rarely closes a door without opening a window. When quantum mechanics enters the picture fully, it offers a radical reinterpretation of what time travel might mean. Instead of imagining a single, fragile timeline that must be protected at all costs, quantum theory hints at a vastly richer structure beneath reality. At the smallest scales, events do not follow a single deterministic path. They explore many possibilities simultaneously. This leads to the idea that the universe may contain not one history, but many. In such a framework, traveling into the past does not rewrite the original sequence of events. Instead, it creates a divergence. The moment an interaction occurs, the timeline branches. Each branch remains internally consistent. Causality is preserved locally, even though the global picture becomes far more complex. The paradox evaporates not because the action is forbidden, but because its consequences are redirected. In this view, the universe does not need to prevent backward time travel entirely. It only needs to ensure that no traveler can tamper with their own origin. The past that produced you remains intact, while your actions unfold in a new branch of reality. The equations remain consistent. Logic survives. The universe does not fracture, it expands in possibility. What is remarkable is that this idea does not come from speculative fiction, but from serious attempts to interpret quantum mechanics. The mathematics does not insist on a single outcome. It allows superpositions, parallel histories, and branching futures. When applied to time travel, these features provide a graceful escape from paradox without requiring censorship by physical law. Even so, the cost of accessing such branching remains enormous. The energies involved, the control required over quantum states, and the interaction with gravity push far beyond anything we can currently achieve. Once again, physics does not say no. It says that the challenge lies not in permission, but in capability. The universe may allow such journeys in principle, but reserves them for civilizations that have mastered reality at its deepest levels. What emerges from this exploration is a striking asymmetry. Forward time travel aligns smoothly with the natural flow of entropy, expansion, and cosmic evolution. Backward time travel, by contrast, collides with the mechanisms that preserve consistency. When allowed, it is redirected into parallel outcomes rather than permitted to overwrite history. The universe seems willing to explore possibilities, but unwilling to erase its own record. This paints a picture of time that is far richer than our everyday experience suggests. Time is not merely a line stretching from past to future. It is a structure with direction, stability, and built-in safeguards. The future is a canvas, flexible and responsive. The past is a foundation, fixed and load-bearing. To disturb it is to risk collapse. And so the universe intervenes, not with rules, but with consequences. In this way, physics reveals a subtle form of wisdom embedded in nature itself. Progress requires openness. Memory requires stability. The laws of time reflect this balance with extraordinary precision, allowing motion toward what can be, while fiercely preserving what already is. As the discussion reaches its most subtle layers, the role of quantum mechanics becomes impossible to ignore. Classical intuition fails us here, because the universe at its deepest level does not behave like a single unfolding story. Instead, it behaves like a symphony of possibilities. Particles do not have definite positions until measured. Events do not choose a single outcome until interaction forces a decision. Reality at the quantum level is not a straight line, but a branching tree. This radically changes how we must think about time itself, and especially about journeys into what we call the past. In the quantum view, history is not a single frozen record carved into stone. It is a tapestry woven from probabilities that only harden into facts when observed or interacted with. This does not mean the past is vague or unreal, but it does mean that the universe is far more flexible than our everyday experience suggests. When applied to time travel, this flexibility offers a way to preserve causality without forbidding exploration. If a traveler would move backward in time, quantum mechanics suggests that they would not enter their own history in the way we instinctively imagine. Instead, they would enter a version of reality consistent with the laws of probability, one that branches from the original timeline rather than overwriting it. This idea resolves the deepest paradoxes not by denying action, but by redefining consequence. You can act freely, but your actions do not ripple backward to erase the conditions that allowed them. The universe remains self-consistent because each timeline carries its own internal logic. From within any single branch, cause still precedes effect. Memory still points backward. Identity still makes sense. What changes is the global picture, which becomes vastly richer and more complex than a single fragile chain of events. What is striking is that this interpretation does not feel forced or artificial. It emerges naturally when quantum mechanics is taken seriously as a description of reality rather than a mere mathematical trick. The same framework that explains why particles can be in two places at once also explains how histories can coexist without contradiction. Time travel, in this sense, becomes less about rewriting the past and more about navigating the immense space of possible histories that the universe already contains. Yet even here, restraint remains a theme. The universe does not allow arbitrary access to these branches, creating conditions where quantum histories diverge in controlled macroscopic ways. Requires an extraordinary level of mastery over matter, energy, and information. We are not talking about machines built in garages or laboratories, but technologies that operate at the level of fundamental reality. The laws are permissive, but they are not generous. They demand precision, scale, and understanding far beyond our current reach. This brings us to a deeper realization about why the past appears so protected. The past is not merely earlier time. It is the accumulated structure of information that defines the present. Every atom, every field, every particle carries a record of interactions that led to its current state. This informational web is not easily altered because it is not localized. Changing the past would require changing not one event, but the correlations embedded across the entire universe. The sheer interconnectedness of reality makes retroactive alteration staggeringly difficult. The future, by contrast, is sparse in information. It has not yet been filled with detail. It exists as a range of possibilities rather than a completed record. This asymmetry explains why physics treats the two directions of time so differently. Moving into the future adds information to the universe. Attempting to move into the past would require erasing or rewriting it. One process aligns with the natural growth of entropy and complexity. The other fights against it. From this perspective, the resistance to altering the past is not hostility, but stability. The universe has evolved mechanisms that preserve coherence across vast scales of space and time. Without such preservation, reality would be brittle, constantly vulnerable to collapse from internal contradiction. Memory, learning, and evolution themselves depend on the past being reliable. The laws of physics reflect this necessity with remarkable elegance. What emerges is a picture of time that is neither rigid nor chaotic. It is structured, directional, and deeply tied to information. The future remains open because it must be. The past remains fixed because it cannot afford not to be. Even when quantum mechanics allows branching, it does so without disturbing the original foundation. The universe expands its possibilities rather than rewriting its history. In this light, time travel ceases to be a mere curiosity and becomes a window into the deepest architecture of reality. It reveals how motion, gravity, quantum uncertainty, and information are woven together into a coherent whole. Science allows us to move forward through time because doing so preserves structure. It resists tampering with the past because structure depends on continuity. The equations do not express preference or emotion, but they encode a profound balance between freedom and order, exploration and preservation, becoming and being. When we step back and look at the full picture, a quiet clarity emerges from all this complexity. Time is not an enemy to be conquered, nor a simple road that can be driven in reverse at will. It is a deeply structured dimension shaped by motion, gravity, quantum uncertainty, and information itself. Science allows us to move into the future because doing so respects the architecture of reality, preserves causality, and aligns with the universe's natural tendency to unfold and expand. The past, however, is not merely behind us in time. It is woven into the very fabric of everything that exists. To disturb it would be to pull at the threads that hold coherence, memory, and meaning together. What physics reveals is not a cruel restriction, but an elegant balance. The universe is generous with possibilities, yet firm about consistency. It invites exploration without allowing contradiction. It permits time to stretch and slow, to carry us forward at different rates while surrounding the past with layers of stability that protect the integrity of reality itself. In doing so, it teaches us something profound. Progress depends on openness, but existence depends on reliability. Without a fixed past, there can be no understandable present and no meaningful future. And perhaps that is the deepest lesson hidden inside the equation. The universe is not designed to trap us in nostalgia or regret, but to propel us forward into what can be discovered, created, and understood. Time, in this sense, is not a prison wall behind us, but a horizon ahead of us one. That invites curiosity while quietly preserving everything that made us who we are. Thank you for watching, and thank you for taking this journey through time, physics, and the deeper logic of the universe.